Hi, my name is John Krochmally, and I've created these video modules for people needing to understand and apply their skills knowledge to install, service, and maintain technology controlled by automation systems, and particularly the Programmable Logic Controller. Programmable Logic Controllers, or PLCs, are frequently found in many applications involving automation and instrumentation. In this presentation, we will cover the way modern programmable logic controllers execute their stored programs. There will be three learning outcomes to this presentation. Number one, relate sequence of operation to PLCs. Number two, state components of the PLC scan cycle. And number three, relate PLC input processing to PLC output commands. We can start to understand the PLC program execution with reference to a simple electrical sequence of operation and the hardwired circuit that could achieve it. One such example is this one. Sequence of operation 2. A normally open push-button PB1 shall control a red light LT1. When PB1 is pushed, the red light LT1 shall turn off. When PB1 is released, LT1 shall illuminate. Designing an electrical circuit to achieve intended operation of the sequence, we might consider the following ladder diagram. In this diagram, we see an applied circuit voltage of 120 volts. The red light LT1 is located to the right of its rung, and the push button PB1 is located to the left. Notice that the PB1 normally open push-button switch will, when pushed, cause the current to flow through itself and then cause the LT1 red light to illuminate. As designed, we can see that this specific diagram will not meet the intended sequence of operation. When PB1 is pushed, the LT1 red light will illuminate. The solution would be to utilize a common relay that contains a coil that becomes an electromagnet when energized, and associated contacts that are normally open and normally closed would respond. In this graphic, we see how this control relay can be wired into the circuit and meet sequence of operation. If PB1 is not pushed, notice that the relay coil between terminals A and B is not energized, and it has not become electromagnetized. In this state, notice that 120 volts is present on relay terminal number 7 and send its currents toward relay terminal number 1, a normally closed set of contacts, and causes the red light to illuminate. Here we see a pushed PB1 causing the relay coil to energize and become magnetized. This causes a mechanical switching action to the related contacts of the relay. Under this condition, what contacts were normally closed become open, and what contacts were normally open to close. Releasing the pressure on PB1 results in the cancellation of the relay coil's electromagnetic effect, and therefore allowing the relay contacts to return back to their normal contact position. Here's another sequence of operation to consider. Sequence of operation 1. A normally opened push-button PB0 shall control a green light LT0. When PB0 is pushed, the green light LT0 shall illuminate. When PP0 is released, LT0 shall turn off. This could be considered easy to do by many, and the solution could be as shown in this graphic. With 120 volts applied to the circuit, when PB0 is pushed, will travel towards the LT0 green light and illuminate it. We could still use a relay to achieve the intended actions as stated in sequence of operation number 1. It could be considered excessive, but it still could be done with the use of a relay. How this could work with a relay is shown in this graphic. Notice that with PB0 not pushed, the relay coil between terminals A and B are not energized and therefore not in a magnetic condition. Notice also that the associated contacts made up by the relay terminals 7, 1, and 4 are in their normal state or condition. Terminal 7 is the common. Terminal 4 is the normally open contact, which, when the relay coil is energized, will close. Pushing PB0, the relay coil energizes, becomes an electromagnet, and then switches the relay contacts. In this example, the green light LT0 turns on. Releasing PB0 brings the relay contacts back to their normal de-energized condition. Using a control relay to achieve the sequence of operation may be seen as over-engineering a solution, but it does work to achieve the sequence of operation. Imagine what a programming logic controller is and what it does. It can be considered a complex relay device that, based on the status of its inputs, commands its outputs on and off. When PLCs are used for device control conceptually, they will always be installed between their inputs and their outputs. Here we see with sequence of operation 2 how PB-1 and LT-1 are hardwired in the circuit utilizing a PLC controller. The central processing unit of the PLC will store created programs and serve as the brains of the system to execute PLC action. Notice that with the sequence of operation number 1, the intended actions are different. The hardwiring of field devices is similar, but the controlling intended actions of the PLC will be determined by the central processing unit's stored program. To understand the execution of PLCs, we can orient ourselves to this graphic, which shows the PLC assembly connected to its input and output field devices. Let's start with the input section of the PLC assembly and related devices. In this graphic, we see that switch S0 is opened, removing any voltages that could accumulate on PLC input module screw terminal 0. Optical couplers located in the input section of the PLC assembly look at the voltage pressure appearing on that PLC terminal and reports this condition to the PLC assembly's processing unit, or central processing unit. The processor sees no voltage on this terminal and records its related memory, A0, as a reference. Closing field device switch S0 causes 120 volts AC to be placed on the PLC input terminal 0. The optical coupler sees this 120 volts AC on the PLC input terminal 0 and reports this condition back to the processor. The processor records this condition as a 1. Also notice on the PLC input module, the associated diagnostic LED 0 at the top becomes illuminated. Let's now look at what happens with the PLC output section. Here we can see that the R0 load will be controlled by the PLC output module of the PLC assembly. Notice that the PLC assembly processor controls an internal switch, here identified as S-0. This is now in an open condition. In this condition, notice that the C0 coil in the output module is in the de-energized state. In this condition, there is 0 volts appearing on the PLC output module's terminal 0, and therefore keeping the related load from operation. Also notice that in the processor, there are memory boxes marked as O output. the numbers in these boxes will either be 0 or 1. If the box on that PLC output, the module has a 0, the coil will not be energized. Here we see the processor causing a 1 to appear in the O output box set. Notice that this 1 appears under the box identified as 0. This command closes the S0 in the PLC processor, causing the related C-0 coil to energize and produce the electromagnetic effect. This in turn causes the associated contacts to close and conduct the applied voltage of the PLC output module to be conveyed to the PLC output module terminal 0 and energize the load. To achieve this method of PLC execution, we can refer to the scan cycle of the Programmable Logic Controllers central processing unit. With the start of the sequence of operation, first order of execution is to scan the inputs. After the scanning of the inputs is done, the PLC then solves the logic, which is stored as a program within the processor. After the logic, which is stored in the PLC's processor, is solved, then the outputs are commanded to position. The last execution in the cycle is to update the PLC memory banks. It is important to understand that the PLC scan cycle will continue its operation, looking at the inputs, solving the logic, commanding outputs, and updating memory continually as long as it is under control of the system. The stored program of the PLC is contained in the processor's memory banks. We consider this to be a virtual environment since they do not have any related physical objects other than the computer chips that it is stored into. The ladder diagram is used to create physical electrical circuits to achieve sequences of operation, and is also used as a foundation to write the program for PLC-controlled operation. In this graphic, we see the electrical diagram on the left. The diagram on the right represents the relay ladder logic programming language to be entered into the processor to achieve the sequence of operation. The relay ladder logic programming language is simply a series of if, ands, else to be used to control output devices based upon the condition of input devices. If something is closed, then command something on, else command something off. Looking at the relay ladder logic program set of instructions on the left, we see that the PB0 push button will control the LT0 green light. The PB0 is wired into the PLC input module's terminal 0. The LT-0 green light is wired into the PLC output module, terminal 0. On the right, we reference the intended sequence of operation. If PB-0 is pushed, then turn on the LT0 green light, else turn off the LT0 green light. Now we can understand how the PLC's assembly and programmed language executes its intended operation. The PLC processor scans the condition of the inputs. Starting on the input section and switch S0 switch, we can see that it is in the closed position, allowing 120 volts to appear on the PLC assembly's 0 terminal on the input card. The central processing unit sees this and enters a 1 in the appropriate memory box. By this way, the associated green LED located at the top of the PLC's input module turns on, indicating voltage on that terminal. The central processing unit then solves the logic contained in its memory banks. The third step of the PLC scan cycle is performed by commanding the outputs based upon the stored program. Here is where the output devices are either commanded on or off depending upon the ladder logic program. The last step in the PLC scan cycle is to update the memory of the PLC central processing unit.